All right, here we go. Hope everybody had a good spring break. So today we're going to look at some more equations, looking more specifically at writing out your skeleton equations. So start with our warm up. Number one, what are the reactants of the above reaction? Right, you should have said that your reactants are methane, CH4, and oxygen, right? Reactants are on the left-hand side. Remembering that your products, right, are the right-hand side. So carbon dioxide and water are your products. All right, number two, what are the coefficient? What will the coefficient be in front of oxygen in the balanced equation above? So we're going to need to balance this. Um, So remember balancing, we're going to write C, H, O. On the reactant side, I got 1 carbon, product side 1. On my reactant side, hydrogen is 4, and product side is 2. Reactant side, oxygen is 2, product side is 2 plus 1, so that gives you 3. All right, then we need to our carbons are good, our hydrogens are not, and our oxygens are not. We're going to save oxygen for last because it has a lone element. So let's try to fix these hydrogens. All right, so my product side is going to need more because 2 is smaller than 4. So I already have 2 hydrogens here, so I'm going to put a 2 in front of here in order to try to make that, right? 2 times 2 is 4. And then on this side, I have 2 times 1 is 2 oxygens plus these 2 here. Right, 2 plus our 2 over there gives us 4. All right, which means on the other side, my hydrogens are now good, but my oxygens are not. I need to put a number in front of here, so I'm going to make that a 2, which makes it 4. So your answer, right, the coefficient in front of oxygen is going to be a 2. Coefficient in front of the oxygen is 2. Some questions that Canvas might ask you, right, if it has a blank space right here for a number, right, that you just need to put a 1 in for that coefficient, right, because 1 is assumed. All right. One more question. What does the parentheses L mean in the above reaction? Right, this is an L. What does the L mean in the above reaction? Notice it here. Right, that L means that it is in the liquid phase. Right, remember a letter in parentheses is just the phase that compound is in. Right, G for gas. If there was an S, that would be solid. And again, AQ means that it is aqueous, dissolved in water. All right, here are the 4 skills you're going to learn in today's notes. All right, 4, that's a lot, but some of them you already know. Right, oh, going back. 2.1 is I know all 7 diatomic molecules, right, which you should already know those. Remember, it's on the front of your periodic table. Your nitrogen, hydrogen, oxygen, fluorine, chlorine, bromine, and iodine. 2.2 is I can identify a physical or chemical change. That we looked at in our last video, which is, right, chemical change means that it has a change like to the actual chemical, the formula makeup of it has occurred, right? Whereas physical is those changes can be reversed. All right, 2.3, we also looked at a little bit in the last video when we looked at that nitrogen triiodine, right? Transforming word equations into balanced chemical equations, right? So that's just taking the compounds that it gives you and making them into the formulas, right? And 2.4, that's the thing that's super new, is I can classify the types of chemical reactions. You got 5 to 6 different types: synthesis, decomposition, single replacement, double replacement, neutralization, and combustion. All right, so that's what we're going to look at first is our reaction types, right? So synthesis is going to be your combination. All right, so I'm going to write down a generic one for all of these with just letters. So synthesis is, right, you got element A plus element B yields compound AB. Right? So two elements come together to form a compound. That's your combination, your synthesis. Decomposition is the reverse of that. It's the breaking down. So you'll start with compound AB, right? And then it'll break into A plus B. Right. So synthesis, right, is like your couple, right? You guys, high school sweethearts, you kind of meet, and you guys become a couple, right? But anything happens, so your decomposition is that couple breaking apart. Right? You had a nice solid couple, but then they break back into their individual parts. Neutralization includes an acid and a base. Neutral, right? That kind of keyword there is that's what it's going to make. Your acid base, when they mix, makes something that's neutral. So we know all acids start with hydrogen. So I'm going to use X as just any generic thing that comes after the H because it doesn't matter. All acids start with hydrogen and a base. I'm going to use generic Y, and then we know a base ends in OH. Okay, so X and Y are just anything that it is bonded with, right? But an acid starts with hydrogen, a base ends in OH, and it's going to yield water, H2O, plus a neutral salt, right? Which is going to be a combination of your X and your Y. Oops, sorry. And that's actually backwards. It'll be YX because positive one always comes first. All right. Combustions, those go boom. They make kind of an explosion, and lots of typically fire is with a combustion. So combustion is any hydrocarbon. And a hydrocarbon is just hydrogen and carbon, right? So any combination, we can put X and Y as our subscripts down here. Any combination of subscripts, as long as it's C and H, in a combustion, your other reactant is always going to be oxygen, and it is always going to yield the same two products, CO2 plus H2O. So oxygen always a reactant, carbon dioxide and water always your products. All right, single replacement is kind of one thing is going to do swapping. So I'm going to use my letters again. So I have A, right? So we have one element plus B, C. All right, and so this is going to yield, right, a new compound and a new element. So what's going to happen is A is going to kick out B. So A is now going to be bonded with C, and then B is going to be left all by itself. Poor little B. Right? This is like when you're going steady with your boyfriend and girlfriend, super happy, and then somebody else comes along and steals them from you. Right? And then they become a couple, and you are left all by your little lonesome. Right? So that's what happens in single replacement is one element comes in, bonds, kicks out one, and then bonds, right? All right, double replacement, you start with two compounds. So this time A is bonded with B, and then C is bonded with D, right? And we have a switcheroo. This is like your swinger couples, right? So A is now going to be bonded with D, and C is going to be bonded with B, right? So, right, they just swapped. A took C's place, C's took A's place. All right, just switches, just like that. All right, you guys should make sure that you have these written down in your notes, those kind of examples. Those will be super helpful and make it easy for you to do your practice later. All right, so we're going to go ahead and try to fill in this chart. This will also help you guys with your practice later. So we're going to start, this is just bigger so you can see it. Which one of our types only have one reactant, right? If it only has one reactant, it gives you a description, right? It breaks up into pieces. That's your decomposition. Oh no. So that's going to be your decomposition. All right. So you start there. If it has one reactant, right, you go over yes, then it's decomposition. If the answer is no, then you go down. Does it only have one product? If it only has one product, right, remember that's your reactants combining to make a single compound. That is your synthesis. All right. So, and if you answer yes, right, only has one product, synthesis. If you still answer no, right, then you ask yourself the question: are the reactants an acid and a base? Right, an acid and a base, right, produces salt and neutral water. Right, so that is your neutralization. All right, so acid and a base are your reactants. It is neutralization. So make sure you guys have those down in your notes. All right, let's fill in the rest, right? So if your answer is still no, you still haven't found out what it is. Is oxygen a reactant and water a product? So is oxygen a reactant and water a product? If the answer is yes, right, that's a hydrocarbon burning in oxygen to produce water and often carbon dioxide. That is our combustion. Right, if your answer is no, still haven't found it yet. So is it an element and a compound make different element and compounds? And so you have one element and one compound. Right? So you have a single element, right, that's going to take the place of another element. That's your swapping. So this is your single replacement. All right. And lastly, if you answered no to all of the previous ones, right, two compounds make two different compounds. Right. If you have two compounds, that is your double replacement. All right. So there are all of your types. Now we're going to look a little bit more at how to write skeleton equations. All right, so we're going to look at this one, which is a synthesis. All right, so write a skeleton equation for when solid zinc reacts with solid iodine to form zinc 2 iodide. All right, remember when we do these, we're just going to go we're going to just start where it starts, right? Go through whenever we run into a compound, right? We're going to write that compound down. So we write a skeleton reaction for when solid zinc. Right? Solid zinc is just zinc, right? So we write down the symbol for zinc, which is Zn. All right, then it says it reacts with, right? Reacts with means we're going to put a plus sign to separate our different reactants. All right, and it says it reacts with solid iodine. So iodine, right, is just iodine, which is I. And then we got to ask ourselves, is it diatomic? The correct answer is yes, so I2. All right, then we keep reading. To form, right, is the next part we get to. To form means that we're going to have an arrow, right? And then it says zinc 2 iodide. All right, zinc 2 iodide is a compound. So a compound, we need to switch our charges. So I have zinc, which has a charge of 2, right, and iodine, which has a charge of -1. Right, so those swap, and then this becomes ZnI2. Right, it just says skeleton equation. Remember the difference between a skeleton equation and a chemical equation is just the coefficients, the balancing part. This one does happen to already be balanced, so it's a skeleton reaction and a balanced chemical equation because you have one zinc on this side, one zinc on this side, an iodine on this side, and an iodine on this side. All right, so there's our first one. Let's see what happens when these two are mixed and water is added as a catalyst. All right, here we go. Here is your first demonstration. Right, so we have zinc. Right, Zn is going to react with iodine, I2, because iodine is diatomic, to form, right, that's your arrow, zinc to iodide. And remember your charges switch, so that becomes ZnI2. So in here I've got some zinc, right, you can see in here, right, in its powder form. Right, and then I2 iodine I've got in here. So what I'm going to do is I'm just going to take those two and mix them. And I'm going to pour the iodine into my zinc. Right, mix it around a little bit, see what happens. Nothing fun really happened. So what we're going to do is we're going to take a little bit of water as a catalyst. Right, so this reaction would happen on its own, but we're going to make it happen a little bit faster by just adding some water. Woo! And there you see what happens with your zinc to iodide. All right, there it goes. That was your synthesis, right? Your synthesis. So you know it was synthesis because you took two elements and you made one new compound. All right. Decomposition. Remember, decomposition is breaking down, right? So you have one compound breaks back down into its two individual parts. So we're going to go ahead and do this one. You guys are going to take a lot more active role. So go ahead and try to write down your reactants and products and see what you get. All right, so let's start with what the first thing it gives us. All right, so going through here, we start with nitrogen trihydride. Right, nitrogen trihydride, so I need to write the formula for that. Nitrogen, there's just one of them. Hydride is hydrogen, tri means three. All right, it says it decomposes into, all right, so that's telling us that it's going to form these things. So you need your arrow, and then hydrogen, right, which is, all right, so hydrogen is the next part it has. Hydrogen is diatomic, so it's got to be H2. And then you have an and, so we're going to draw a plus sign to separate them. And then lastly, we have nitrogen, right? So N2. All right, so NH3 yields H2 plus N2, right? Again, skeleton equation because it is not balanced, right? This one is not balanced too. All right, that was your decomposition. So now let's look at single replacement. So remember, single replacement, you have a single element, and then they break into the so you have a single element in a compound, and that single element is going to replace the other one of the elements in the compound, and then that element it replaced is going to be by its lonesome. All right, so go ahead and try to write down your reactants. All right, all right, first reactant, right, it says solid aluminum. All right, so aluminum is just Al, not diatomic. So it's going to, just be Al. All right, reacts with, so plus aqueous copper 2 chloride. All right, that's compound, so we need to worry about our formulas. All right, so Cu plus 2, chlorine Cl minus. All right, those two swap, so it becomes Cu Cl2. All right, and then to form, all right, so then we know after that is going to be our products. So our products are going to be copper, right, which is just Cu, not diatomic, and aluminum chloride. Whenever you have a compound, remember you got to swap your charges. So I have aluminum has a charge of +3, chlorine has a charge of -1, so those two swap. So it is AlCl3. All right, there you go. Again, skeleton equation because it is not balanced. So we can balance it. Let's go ahead and do that for fun. All right. So remember when you balance, you have AlCuCl on our reactant side. We have 1 aluminum. On our product side, we have 1 aluminum. On our reactant side, we have 1 copper. And on our product side, we have 1 copper. Actually, I'm going to do something different. And then Cl on this side, we have 2, and on our product side, we have 3. All right, so the only thing that is not, right, now is our Cl. All right, so we're going to go ahead and try to, right, fix this. All right, so on this side, right, we need more. We can't put a 1 here because it doesn't add, right? It multiplies. So if I put a 1 here, 1 times 2 is still 2. So I'm never really going to be able to make this side chlorines be a 3. So I'm going to have to do the denominator, right? So I'm going to put a 3 here, right? And that's going to change our chlorines on this side to 6. Remember, you can't put this coefficient in the middle of here to only apply to the chlorine. You have to put it in the front of the whole compound. So that means I also now have 3 Cus. All right, now I can go back to the other side and fix my chlorines, right? I'm going to need to put a 2 here, right, to make these chlorines 6. But that also changes my Al. Now I have 2 Als. But that's okay, because we can still do more things, right? So on this side, I'm going to put a 2 in front of my Al. Right, and then the only thing that's not fixed still is our coppers, so I can put a 3 here. Right, there we go. All right, so that is a balanced equation. All right, let's see what happens with this reaction. All right, here we go. Single replacement reaction. So I have aluminum, which is just Al, reacts with, so plus copper 2 chloride. Remember your charge is switch, so that's CuCl2 to form, right? Copper is its lone element, so just Cu, and plus aluminum chloride. Again, charge is switch, so AlCl3. Alright, so I've just got my ball of aluminum right here, and just a little ball of aluminum foil, which is straight aluminum, and in my beaker I have some copper 2 chloride, nice pretty blue color. So we're going to pop that in there and see what happens. So you can see there's definitely a reaction happening. There's some steam coming off. This beaker's getting warm. You can see the steam, like that condensation forming. So there's definitely some kind of chemical reaction happening. And what in the world is happening in the bottom? Looks like it's snowing in there. Something's falling? Let's see. So from the top you can see that guy's really steaming. So if I pick this up, look at what happened to the bottom of my aluminum foil, right? The part that was touching it. What do you think? Why is it that color? Right? What happened? If you're thinking it burned, not exactly. Remember what our reactants are. So our reactants are pure copper and aluminum chloride. I meant products. So you can see in here our color is getting not so blue anymore. And this happened, right? So our aluminum has replaced the copper in the copper 2 chloride, and now this is turned into copper, right? This is the color, right? If you think about a penny, that's exactly the color that a penny is. So what has happened is that copper, right, is now all by its lonesome, so you can actually see that copper color, right? And that's what's happened. Right, down here in the bottom, right, there's all this copper that has fallen off. Cool. So that's your single replacement, right? The aluminum replaced the copper, taking the copper out, which is why we have this copper color. Sweet. All right, so that was your single replacement, right? Our aluminum got replaced at the copper, so then the copper was left all by its own, and that was that copper color that you guys could see in the video. All right, let's try a double replacement. So you guys go ahead. Right, it says skeleton equation for when lead 2 nitrate is added to potassium iodide to form lead 2 iodide and potassium nitrate. Go ahead and try to write out your reactants. All right, here we go. Reactants. All right, so lead 2 nitrate, Pb2 nitrate is NO3 -1. All right, those two swap. So PbNO3 parentheses 2. And it says is added, right? So that's going to be our plus. And then our second one is potassium iodide, which is Ki. Right? Potassium has +1, I has a -1, so they swap. This becomes Ki. Right? To form. Right, so that's going to be our arrow that separates. And then our try to go ahead and write your products. So our product, first one is lead 2 iodide. Pb plus 2I -1. Right, they swap. PbI2. Right, the number one problem mistake that people make on these is they want to just keep the subscripts, right? They want to write PbI because that's what is here. But every time, even with your products, you have to redo and write down your formulas. All right, and then so we're going to separate it with a plus sign. Our last one is potassium nitrate. So K is +1, nitrate is NO3 with a -1 charge. When they swap, that is just KNO3. All right, so again, this is your skeleton equation. Let's go ahead and balance it for fun, right? Super fun stuff. All right, so I have PB, I have NO3, I have K, and I. All right, so on our reactant side, PB, there is 1. Product side, there is also 1. Nitrate, right, is 2. And on this side, nitrate is 1. K is 1. And K is 1 on this side. Iodine is 1 on this side. And iodine is 2 on our product side. All right, so NO3 and I are not quite where we want them to be. They're not equal to each other, right? So it doesn't matter which one you start with. I'm going to go with I just because. So I'm going to put a 2 in front of this, and that makes this 2, and it makes my K 2. And then, right, I have NO3 and K are messed up, but, oh, they're together on this side. So I'll put a 2 there. That makes my K 2, makes my NO3 2. All right, and ta-da! You have a balanced chemical equation. Good stuff. All right, so let's see what happens. All right, time for a double replacement reaction. So we've got lead 2 nitrate, right, which is PbNO3 parentheses 2, right? Remember again, charges reacts with, so plus potassium iodide, which is just going to be Ki, because both of them have a charge of 1, to form, so that's going to be our yield, our arrow, lead 2 iodide, PbI2, and plus potassium nitrate, KNO3. All right, so we can see here is our lead nitrate, Right, clear for the most part, but you can kind of see that there are some crystals in the bottom, so it's not all completely dissolved. And then Ki, you can also mostly see through this bottle, enough to tell that it is clear, like pretty colorless. So now what we're going to do is we're just going to mix these two together. So I need to open my Ki bottle. And I'm just going to pour this in here, and we're going to see what happens. Ooh, well, that's a pretty color. Right, so there's one indication of chemical change. Another one, maybe you can see if I get up in here real close. Right, there's a good picture of it. It looks right, clumpy or cloudy, right, and you can totally see it on the bottom. Right, in there, that's not a liquid anymore. That is solid. Right? And if I were to kind of pour off, if I could filter it well, or if I let this sit long enough, you'd notice that the water is still clear, and it's that solid that is that yellow color. Right, so remember, we formed two completely new compounds. We formed lead iodide and potassium nitrate. Right, so if you look at your solubility. All right, I'm going to skip that because we actually haven't talked about those rules yet. But do remember, right, notice how it's lead 2 nitrate and then potassium iodide, and see how your lead and your potassium swapped places, right? And your products, lead is now bonded to iodide and potassium is bonded to nitrate, right? So those two metals just swapped places. All right, that's it. So you guys should be able to do your practices now. You got this.